So now we're going to begin conservation of momentum for a control volume. And recall that momentum, which is Newton's second law, is given by the time rate change of momentum is equal to the sum of forces, or dp dt, and the p vector is just mass times velocity. And you guys have been using that all the time. And recall that for a volume, or a control volume really, we discussed two types of forces earlier in this class. One was body forces. Those occur inside of the control volume. Weight is the most common one that we'll be dealing with. But if you work for, say, fusion energy for one of the national labs, you could be dealing with magnetic forces and and a few other body forces. And there are also forces that occur on the surface of the control volume. And the one we'll be dealing with most often is pressure. And just recall that pressure is minus p n hat dA. So if we have our little surface here, or our little volume here, we would have some n hat pointing out and some pressure pointing in. And this pressure would be all around the surface of this object. And for the body force, we could have some W acting downwards. Okay, but just remember, in general, just as we did in fluid statics, if you wanted to find the pressure forces, you need to find the entire pressure field on the surface and even all the surface patches, and basically add them all up. And there is also a viscous stress that can act on the surface of the object, and we dealt with that way back in chapter 2. Okay, so, and also there is a third type of force. There are also external forces. Okay, and these are if you have some sort of external force, like something impacting, like a plate pushing on the fluid or something like that. Okay, so there are external forces too. But in terms of the traditional fluid mechanical forces, we only have surface and body forces. Okay, and so just recall that that the vector of momentum is just mass times velocity. And if we want to find the entire amount of momentum in this volume here, it is just the integral of density times velocity in the entire volume. Okay, and then if we want to use the Reynolds transport theorem, we need to define an eta such that these two integrals here over the volume are equivalent. And you can see that if we set eta equal to the velocity vector of the fluid, we basically satisfy that. So this directly implies that eta, if you want to apply the Reynolds transport theorem, to turn Newton's second law, which you guys have been dealing with, that follows a particle around to Newton's second law for a control volume. Okay. And I will add here that this weight is just the integral over the volume of rho g dv. Okay. Now recall that for a particle, then, using all three of these types of forces, we could have that the time rate change of momentum using the Reynolds transport theorem, that basically this derivative here, this time rate change of momentum, RF, or mass times acceleration, this is the Lagrangian form of it. And this here is the control volume version of the same derivative. Okay, and so we have the time rate change of accumulation of momentum inside of the control volume, and we have the net amount of momentum leaving through the control surface. Okay, and now unfortunately, unlike conservation of mass, this is not equal to 0. It is equal to the sum of the forces acting on the control volume. Okay, so the right-hand side of this is not 0. It is equal to the sum of the forces. So if I'm going to rewrite this out now, let's see. So we had that for the particle, we have the sum of the forces, and we have the body forces acting in it, the surface forces, and also any external forces that are pushing on it. So now we apply those to the control volume aversion, and we have that dp dt is equal to partial t of the volume integral of rho v dv plus the area integral over the control surface. Got to get that right, over the CV, plus the integral over the control surface of v rho v dot n hat dA is equal to the integral of all the body forces, and that's a volume integral over the control volume. Fix that. And the reason that we do the integral is that maybe the density is higher over here than it is over here, and we would actually need to integrate them. Okay, and then we have surface forces acting on the control surface, and also we have and we can also have some external forces pushing on the control volume. Okay, so this term here represents the net body forces. This term here represents the net surface forces, integrated over the entire surface of the object, and this term here represents the net external forces. Okay, and this term here is the net accumulation of momentum in the control volume, and this term here is the net amount of momentum that is leaving through the control surface. Okay, so we can have, so just as mass can leave through the control surface, it also carries along with it momentum. And so that also leaves through the control surface. Now this form here is valid for a non-moving or a stationary non-deforming control volume. Okay, because this does not involve any of the relative velocities. Now, oops, sorry about that. How do we apply this to a moving but non-deforming control volume? Deforming control volumes with conservation of momentum can get kind of complicated, and we will not be dealing with those in this class. Well, recall that essentially for the control volume, or for the deforming control volume, this V here in the conservation law, we replaced with the we replaced V with the relative velocity Vxyz. And so that's essentially what we do here. We replace this V with the relative velocity. Okay? And so Vxyz is just the fluid velocity minus the velocity of the control of the control volume or the control surface. And then also note that if our control volume is non-deforming, so if we have a control volume and it is moving but non-deforming, it's essentially maintaining its shape. So the velocity of the control volume at any point inside of this control volume and on the surface is identical. So that means that the velocity of the surface is equal to the velocity of the control volume. And that's only if they are non-deforming. If this is deforming, then basically that means like this part of the surface could be moving up faster than a point inside of the control volume. And so recall that for a deforming control volume, the generic version of the RTT for a deforming control volume was just this, where we had the accumulation of eta in the control volume plus the net amount of eta leaving through the control surface, and this V here was replaced with the relative velocity. Now for here, it might be tempting to just put the relative velocity here, but that's incorrect because momentum is conserving momentum. And so we actually need to use the fluid velocity. Okay, but we can use the definition of the relative velocity and then solve for the fluid velocity and substitute that in. Because to keep things straight, we would like a relative velocity here and a relative velocity here, and we're going to work towards that. But when we do that, there will be a very interesting extra term that pops out of it. Okay, so we work with this a bit more, and the fluid velocity then, just solve this for v, is just equal to the relative velocity plus the velocity of the control surface. Okay, so for momentum with the moving control volume, eta is equal to the fluid velocity, and that's equal to the relative velocity plus the velocity of the control surface. Okay, so now we're going to take this and substitute that into eta. Okay, and I'm going to substitute that into, oops, wrong one. I'm going to substitute that into here, and I'm going to substitute that into there. And in doing so, we get this expression here that looks like a mess. This is actually not over the control surface, it's over the control volume. And so, again, we have, in our right-hand side for momentum is the sum of the forces. So we have essentially made a huge mess of it. But we can work with this, and a lot of these terms will basically simplify out. Okay, so first we will work with this term here. Okay, and so I'm just gonna work with this down over here, and what we do when we do that is we have that this integral here. I'm basically going to separate this into two separate integrals here. So this here is looking like something that we want. We want to make it easy to use. We want the relative. We just want to use one velocity everywhere, and that would be the relative velocity. So we don't need to keep track of. We use the fluid velocity here and the relative velocity here. It is nice to use one velocity everywhere, but still account for a moving control volume. So this here is a term that we want. And we got to add this term over here. So this is the velocity of the control surface, rho v xyz dot n hat dA. Now, if it's non-deforming, I just argued that the velocity of the control surface is spatially constant. So if it's spatially constant, that means it is not a function of position on the surface, which means we can basically yank that out of the integral. Because the velocity of the control surface, constant is the wrong word. It's not a function of position. Okay, so we can then work with that, and then this, then doing that, this expression becomes, we don't do anything with this first term. And I just pulled the velocity of the control surface out because we're assuming that is spatially uniform. And then we have this term here. Okay? And so it looks like we've sort of done nothing, and we've, again, made a mess of it. But recall, this integral here is actually in conservation of mass. So recall that conservation of mass is given by a partial t of the volume integral of density over the control volume plus this integral right here, and that's equal to 0. So why don't we take this integral here, or why don't we take this conservation of mass and solve for this integral here? Okay, so this implies, and then doing that, this implies that this net mass flux out through the moving control volume is equal to minus partial t of the integral of density over the control volume. Okay, so I can take this expression here and substitute it into here. Okay? And so when I do that, this entire expression here becomes this first integral over here that is unchanged minus the velocity of the control surface times the velocity of the control surface times a partial t of the mass inside of the control volume. Okay? So now we have now worked with this integral here, and I can substitute that in. So I'm going to substitute that in there. And we wind up with this. Again, you have to bear with me on this. It seems like we're making a pretty huge mess, but this will simplify to something fairly nice later on. So we have this term here, which just represents the net accumulation of momentum inside of the moving accelerating control volume. We have the net flux of momentum out through the control volume, and we have this extra term here that came, that basically popped out. So now, and again, it looks like we've gained nothing from this. Okay, so now, let's work with this a bit more. And what I'm going to do is I am going to now work with this term and split it into two integrals, just like I did, basically just like I did with the surface integral term. So I'm going to do that. Then what happens is I split this into two integrals. I have the integral of partial t of vxyz rho dv plus partial t of the integral of the velocity inside of the control volume of rho dv plus the integral of this stuff here. Okay, but now we can work with this term here a bit, because this term is a term that we like. So we have a surface integral of eta involving the relative velocity, and a surface integral term here of also eta involving the relative velocity. There's now no need to keep track of which velocity is which. We just need to figure out what to do with these two terms here. Okay, so we're going to do that, and we're also going to note that if the control volume is non-deforming, then that means the velocity at the control surface is equal to the velocity of the control volume. So these both are the same, and they are spatially uniform. I basically argued that if we draw a little random volume, this is basically saying that the velocity not of the fluid, but of the volume itself as it's moving through space, is identical everywhere on the surface and inside of the inside of the control volume. Okay, so we can then work with this term here, and since it's not spatially uniform, we can basically pull that out because it's spatially uniform. We can pull that outside of the integral, but it can be time varying, so we cannot pull it all the way out. We can only pull outside of the integral. So then this turns into partial t of the control volume velocity times the integral of rho over the entire control volume. So I'm going to use the product rule here. And what we wind up with when we do that is we wind up with the velocity of the control volume times the time derivative of the volume integral of rho inside of the control volume plus dv dt of the control volume times the integral of density, or this is really mass. Okay? And so notice that because we are assuming a non-deforming control volume, this control volume velocity is not a function of space, which means it is only a function of time, so we can basically exchange the partial derivatives for ordinary derivatives. So now we're going to take this result here and substitute it into this time derivative here. So I'm going to do that. And again, it looks like I'm just making this big giant mess of everything. But what we find here, after we expand everything out, we find that essentially this term over here, which was introduced here, is equal and opposite to this term over here. It's not zero; they're just equal and opposite, which was introduced when while we were working with the surface integral term. Okay, and note that the velocity of the control surface is equal to the velocity of the control volume. So basically these two terms here are the same. Okay. So now we've actually gotten rid of most of the terms. And notice that the only terms that survive are this term here, the sum of the forces, and this term here. But this term here has a very interesting interpretation. This here is acceleration of the control volume. And this here is mass. So basically, this term here is the mass times acceleration of the control volume itself. Okay, so this implies that, putting everything together here, that our full Reynolds transport theorem for an accelerating but non-deforming control volume is equal to this expression over here, where we have partial v partial t times the mass. This term here is just the mass, because mass is just the integral of density over the volume, plus the integral of the relative velocity times rho dv, and actually there should be a partial t. Okay, plus the integral through the control surface of vxyz rho vxyz dot n hat dA. That's the net amount of momentum that is leaving the control volume through the control surface, plus the sum of the forces. So we have body forces, surface forces, and external forces in general. Okay, and as I said before, this term here, it just represents the acceleration of the control volume. Okay, and so when you're working with momentum, you have to be careful if you're dealing with a moving control volume, that you can't just set the velocity. You can't just replace the velocity with the relative velocity in eta. When you do that, you have an extra term. And this term here is for the acceleration of the control volume. Okay? And so in your homework, I expect you to start from this form and cross out terms that you don't need. So if your control volume is not accelerating, I expect you to basically show explicitly that it's not accelerating. I don't need that term. If your control volume is non-moving, you can just say Vxyz equals V and just end it with that. And this will work for basically all the cases. Okay? But however, note there are restrictions to this form, and this is valid for, one, a non-deforming control volume, but the control volume can accelerate. And we'll give an example of an accelerating control volume when I do a bunch of examples later on. And the acceleration of the control volume is relative to a stationary frame where the velocity of the control volume is zero. Okay? And then I'm just going to summarize that the body forces, in general for this class, that equals sum of F body. So that's just the integral of rho g dv of everything inside of the control volume. We have surface forces. And in general, that's pressure and viscous stress. You can have other surface forces too, but we won't discuss those in this class. Okay, and so that means that sum of F body equals minus plus F visc. And we are not going to discuss much more about that at this point in this class. Okay. Okay, and then I will make a note, and we're going to encounter this quite a bit, that if on the surface of the control volume the pressure is atmospheric or it's completely uniform, that is, the pressure is the same everywhere on the surface, there will be no net pressure forces pushing on it. Okay, and you can prove that is that by basically working with the integral of p n hat dA. Well, let's just say that our uniform pressure is atmospheric pressure. It doesn't have to be atmospheric pressure, it just needs to be uniform. So that equals the surface integral of the atmospheric pressure times n hat. Okay, and so that is the pressure that is pushing everywhere uniformly on the surface. And here I can use the gradient theorem and turn the surface integral into a volume integral of the gradient of the pressure over the entire volume. Well, guess what? This is a constant. It is completely uniform, and so the gradient of a uniform scalar is 0. So essentially, this is just a quick little proof that if you have a constant uniform pressure on your control surface, there is no net pressure force pushing on it. Okay, so that means that the net pressure forces are equal to 0. And that's something that we will encounter quite a bit. Okay? So now I will give an example of how to apply conservation of momentum, and we will gradually ratchet up the complexity. So first we will start with a stationary control volume, and this is related to one example that I gave for conservation of mass. So here's our example, is that we have a tube, and at the bottom of the tube we have a velocity profile coming in from the bottom, and it's completely uniform at some velocity v1, and we have a velocity profile leaving it due to the no slip condition that is occurring on the walls of this pipe. We have gravity acting downwards, and we have the total length of the pipe between these two stations is given by L. And this velocity profile is given by A times 1 minus small r squared, and r is just the distance from the center line, and cap r is the radius of the tube. Okay, and so we are also allowed to assume that the pressure is uniform at every elevation. Okay, so that means that along this red line here, that the pressure is the same over here as it is over here. And the pressure is the same over here on this red line as it is over here. But the pressure over here and the pressure over here along a vertical line is different. Okay, and we are allowed to treat the frictional forces as just some random frictional force that we don't know, that we're not going to do anything else. We're not going to do anything else with that. Okay, we will be dealing with that properly later on in chapter 8. Okay, and so what we are asked to find is the pressure difference between the bottom and the top, delta P. Okay, and it turns out that what happens is, even if we turn the pipe sideways and there was no positive or there was no negative effect of gravity, is that the frictional forces of viscosity of the fluid sticking to the wall would actually cause the pressure to decrease as the fluid flows down the pipe, and that's why you need pumps to basically move the fluid through the pipe and keep it moving. Okay, and so for this we need to make a whole litany of assumptions, and again you need to list these out. And so where we will assume that the flow is steady, we'll assume a stationary non-deforming control volume, which means that the velocity of the control volume is 0. We'll assume that the flow is incompressible, and we'll assume constant properties, and we will also assume that there's no leaking through the pipe walls, or that they are impermeable. Okay, and so now we can go through the solution. So first of all, we need to find A, and we kind of already did that, but I'll do it again for the sake of completeness. So we need to find this parameter A, and we can use conservation of mass to do that. Now, in general, when you use conservation of momentum, you're also going to have to use conservation of mass as well. Is that you almost always have to use those together. Okay, so we will work with conservation of mass. And so to find A, and conservation of mass states that the time rate change of mass in our system is equal to, in control volume form, that is equal to the partial t of the volume integral in the control volume of rho dv plus the integral of rho times the relative velocity dot n hat dA. And I do want you to start from this generic form every time, even though the control volume is stationary. And then I just want you to make a little argument that because it's steady, we can just say that Vxyz is equal to V minus VCV, which this goes to 0 because the control volume is stationary. And also it's steady, so we can cross out that term. Okay. So now we can work with this a bit more. And so basically this entire expression here reduces to this integral here. Well, we're assuming constant properties, which means we can yank out the density. And then when you do that, the density multiplies the integral. And essentially what we wind up with is that the integral of v dot n hat dA over the control surface is equal to 0. And now, as always, we need a control volume. A control volume for this type of problem is every bit as important as it is as a free body diagram is in statics or mechanics of materials or dynamics. Okay, so I'm going to call this station, oops, wrong one. I'm going to call this station 1, and I'm going to call this station 2. Okay, so we have some velocity of v1 here, and we have n hat 1 pointing straight down. At station 2, we have the actual velocity profile right here, and we have n hat 2 pointing up, and we have the actual velocity profile. And we have, and I'm going to call station 3 just the walls of the tube. And again, they're impermeable, so they're not going to have any contribution to that integral there, period. Okay, so we have our control volume drawn, we have our n hats drawn. We are following the proper procedure for walking around the control volume, and n hat points to the outside on both surfaces and even on the third surface. Okay, so now we can work with this. Now we can work with this integral here. We basically split it over to the three surfaces. So we have to integrate v dot n hat over this surface here. We have to integrate v dot n hat over this surface here, and we have to integrate v dot n hat over the walls of the tube. Well, there is no leaking through the pipe, and that implies that Vxyz dot n hat is equal to 0. Okay? So that term goes bye-bye because there's no leaking. Okay? So now, as we did before, we just essentially work through all of these faces one by one, and this is really a matter of bookkeeping. Okay? So face 1, we want to form this integral over here. And we know that V1 is some flat uniform profile of V1, and I'll call this distance here, or that direction, y. And that is going up, so that is V1 j hat. And n hat 1 is pointing down, so n hat 1 equals minus j hat. Okay? So we have the velocity vector 1 is equal to V1 j hat, n hat 1 is equal to minus j hat, and then their dot product is just equal to minus V1. Okay, so this implies we can start stuffing these into this integral over here. This implies that this area integral here is just the integral of minus V1 over the area, and that's uniform. We can pull that out, and that winds up being minus V1 dA1, and the area is just pi r squared. Okay, so just to put everything together, we have that this integral here is equal to minus V1 pi r squared. So of this nasty surface integral, we know this piece here. So now we need to work with phase 2. And phase 2 is given by the integral of V2 dot n hat 2 over the area. Well, V2, I'm going to scroll back up again. That is going up, so if I'm to make it a vector, that would be this a times the quantity 1 minus r squared over cap r squared in the j hat direction, and n hat 2 is just equal to j hat. Okay, because again, it's pointing straight up. Okay, so I just sort of keep tabs on that here. And then the integral needs their dot product. So I'm going to do that. And so now we need to do, so now we can take that, put that into the integral. Now for the integral, again, we're going to need this is not uniform. So when we put this into this integral here, we cannot pull it out. Instead, we are going to have to integrate over rings like I did for conservation of mass. And I'm gonna go through the argument rather quickly. But again, we can just integrate this over infinitely thin, an infinite number of infinitesimally thin rings. And the area of those rings is 2 pi r dr. Okay, so then we start stuffing this stuff in. We have the integral of v2 dot n hat 2 dA2 is just equal to the integral of this function here times the differential area over this entire area. So it's just the integral of this over r. And we did this integral before. I will unmask the answers or the intermediate steps, but I'm not going to discuss them in detail because it's just a straightforward integral at this point. Okay, and we just get pi a r squared over 2. So now we can put everything together for conservation of mass and show that basically this integral, and actually that should be closed and that should be over the control surface, k is equal to 0. And that equals this first integral here, which we found above, and this result over here. So I can substitute that in. And the first result was minus v1 pi r squared plus this result over here, which is pi a r squared over 2. The pi r squareds cancel out, and I can solve for a. And when you find that, a is just twice the velocity of the fluid coming out. So basically, a is the peak velocity u max in the previous problem, and v1 is just the average velocity. Okay, and we will be actually using that a bit more later on when we get to chapter 8. Okay, and so this implies that v2 is now, we can actually put that in terms of v1 in the radius. That's just twice v1 times this function over here. And it's acting in the j hat direction. Okay? So now, we know A. I redid quite a bit of work to get that, but it sort of bears repeating again. Okay, so now, if we want to find the pressure drop, we need to use linear momentum. To find the pressure drop, and I'm going to apply that in the vertical direction. So now, as with conservation of mass, I want you to start with the most generic form that I have written down. And so we have the time rate change of momentum is equal to this term here, which is the acceleration, which is the mass times acceleration of the control volume itself. This term here goes to 0 because we have a stationary control volume, plus this term over here, which is which is partial t of the volume integral over the control volume of rho vxyz dv, and because we're assuming steady, this term is also crossed out, and we are left with this term here, which is the surface integral of vxyz rho vxyz dot n hat dA, and that's equal to the sum of the forces acting on the control volume. And because the control volume is stationary, vxyz is just equal to the fluid velocity. Okay, and so we could really just make that the sum of the forces then is equal to the surface integral of v rho v dot n hat dA. Okay, so now, so those are the terms that we need to put in, and now we need to do a control volume, or a free body diagram, and another control volume for this. Okay, so what I like to do for these problems is I like to have an acceleration diagram on the left side and a free body diagram on the right side. Okay, and so here again, all we do is we keep track of the velocities and the densities and basically everything like that. And I'm just going to not draw the rake here for the velocity. I'll just say that this is v1 j hat, and n hat 1 equals minus j hat. Okay, and we have the velocity profile for 2. That's basically just this function here that we found above, and n hat 2 equals j hat. Okay, and so on the diagram on the left, I like to keep tabs on basically everything here, because basically this term here represents dp dt, and then I like to put the forces in a separate diagram, and I like to put that on the right because this diagram over here it just represents the sum of forces acting on it. Okay, so what forces do we have? Now the control volume is just inside of the pipe. Okay, so what forces do we have? Well, we're told that we have frictional forces, and those frictional forces oppose the motion, so those act downward. We'll have weight of the fluid acting downward, those are body forces. And we have pressure pushing up from the bottom, and we have pressure pushing down from the top. And we're told that the pressure is uniform over all of these surfaces. Okay, and also right now we're only conserving momentum in the vertical direction. But if we wanted to be very rigorous, we would also consider momentum in the radial direction as well. Okay, but it turns out that essentially has no influence. Okay, so now, based on the free body diagram and our earlier result, that the integral over the control surface, and I'm going to move this over to here, and I'm going to scooch these over to here. Okay, and so dp dt for that reduced to this surface integral here, and the sum of the forces acting on it turned into this, turned into that expression here. Okay, so we got the pressure forces, and the pressure forces are always given by the integral of minus p times n hat over the control surface. Okay, so we have the weight going down, we have the weight going down, we have the frictional forces going down, and we have we have the pressure forces acting on that. So we need to find basically this integral and this integral. I warned earlier in class that we're going to be doing lots and lots of surface integrals. And so this is essentially the portion of the class that involves lots and lots of fun surface integrals. I said that, of course, with lots of sarcasm. So we need to find these two integrals here. So let's do the same thing that we did before. We can basically break this into the three different pieces. I'm not going to explicitly expand that out. You should probably do that in your homework, just to do the good bookkeeping. But basically, we then walk around the control volume, and we basically form the integral, making sure that we complete the surface. Okay, and so again, like I did before, we just keep track of everything. And so from before, we know that v1 is v1 j hat, and n hat 1 is minus j hat, and basically v1 dot n hat 1 is minus v1. Rho 1 is rho. That does not cancel out like it does for conservation of mass. So we actually need to know what that is. So rho is constant, so the density at station 1 is just the density. So then we need to form this integral here, and we substitute in our results. And actually this one here is wrong. v1 j hat. Okay, and so this winds up being v1 j hat times rho times minus v1 dA1, and that is equal to minus rho. These here, all this stuff here is completely uniform. We can pull that out of the integral. Okay, so we can pull that out, and that equals minus the integral of dA1, and I'll erase this. And I did forget to do the j hat. Okay, just to indicate that it's pointing in the j hat, that this force is pointing in the j hat direction. So now we have the integral of v rho v dot n hat dA over the bottom surface, which is right here. Now we need to do the same thing for the pressure forces. Fortunately, we know that the pressure is completely uniform at any elevation. So basically, that means that the integral of minus p1 n hat dA1 is essentially basically minus p times n hat, and these are both constant. I can yank them out. N hat 1, I'm going to move these over a little bit. minus P1 times minus j hat, which is n hat 1, times the integral of the area. And we have a minus here and a minus here. And we wind up with that the net pressure force on the bottom face is P1 A1 times j hat. And so that basically means it is pushing up from the bottom. And so that all, so our n hat convention makes sense not only for flow rates, it also makes sense for pressure forces. Okay, because it basically makes sense that the pressure here is pushing up from the bottom. So if we came up with the wrong direction, we would we know that we basically messed up somewhere. And then I just use the result for the area, that it's pi r squared, and I get our final result for the pressure. Okay, and I do the same thing for phase 2. Phase 2 is a bit more complicated because it is not uniform. So we actually have to do a surface. So we actually have to do an area integral, and we use our result from conservation of mass, and we find that V2 is twice V1 times the quantity 1 minus r over r squared j hat, and hat 2 is j hat. We can go through and find their dot product again like we did before, and we know that the differential area, because we need to integrate over the same rings. It's just now our integral is a little bit more complicated to deal with. So then we have that the integral, that our integral here, we can start to substitute everything out. And the only thing here that we can pull out is the density, because the density is constant. Nothing else in here is constant. Okay, and so basically ρ2 is constant. We can yank that out, and then the integral becomes slightly simpler. And now I just substitute in our result for V2 into here. We got our nasty expression here that we substituted in. Don't forget the j hat. And we have our dot product here, and we have dA over here, and we basically integrate that over the entire radius, or the entire area of the tube. Okay, so I'm going to uncover those intermediate results, but this implies, again, here we're just working with an integral. It is fairly straightforward. It's just a polynomial. It's not a fun polynomial to work with. It's tedious, and so I'm just going to skip to the final result. But what we find out is that this integral over here just becomes 4/3 pi r squared times v1 squared j hat. Okay, and then we can do the exact same thing for the pressure as I did before. It's just the same thing because pressure at station 2 is also uniform, because we are told that it is completely uniform, and so you can do the same thing. And so the integral of minus P2, I should, for conciseness here, I should pull that out, just equals to minus P2 times pi r squared j hat. And the reason that that is negative here is because n hat 2 is j hat, and so we have a negative here and a plus sign here. Whereas for the other surface, it was positive because we had the negative sign in front of pressure and a negative sign in front of, and the n hat was also pointing downwards. So those two negatives canceled, but here we only have one negative. Okay, so now we know all the pieces. And again, in your homework, I would expect you to show that the integral over A3 of v rho v dot n hat dA is equal to 0. Impermeable walls. Okay, and so I would expect you to show that in your homework. So now we need to find the weight. And the weight is just the integral of basically rho times g dv. Well, rho is constant, g is constant. We can yank those out. And that is just equal to density times gravity times the integral of dv over the volume, which is just the volume. And the volume of the pipe is just the cross-sectional area of the pipe times its length, and the length between the first station down here and the upper station here, this here is given by the distance L. Okay, so we now know the weight, and that is in the minus j hat direction. Okay, so now we know all the pieces. We know the surface integral. Here we can basically form this now. We know the weight. We know the friction force. Well, we're just told to call that F fric. And we now know all the pieces to that integral. And then I will make a note. I already noted about this, that the integral over the third area, or the pipe walls, is 0. And also the integral of the pressure forces on the walls of the pipe are also 0. And the reason that is if we do a bird's eye view at any station of the pipe, and we look at the walls, is that the pressure, and we do the control volume just slightly inside, the pressure on any side of the control volume, because the pressure is completely uniform, we have the exact same pressure pushing over here that we do over here. So in other words, the pressure basically pushing to the left is countered by the pressure on the right. Okay, and so basically this integral here is 0, and you could also use something similar to the uniform pressure argument. Okay, and so basically this here is also to 0. Okay, and again, we need to do these extra sides here because we need to completely close the volume, and these aren't closed, and these areas aren't closed. Okay, because again, this circle here means that we need to close we need to close the area integral and integrate over the entirety of the control surface. Okay, and the control surface must be closed. So now we just use our results and basically add them all up. So then we have the integral of this over area 1, the integral of this over area 2. We have the weight, which I'm going to use that result here in a little bit. We have the frictional force acting downwards. We have the pressure force pushing up from the bottom, and the pressure force pushing down from the top. And these are all, and notice these are all in the j hat direction. So I'm just going to stop using j hat to just note that this is in the j hat direction, and I'm going to do some rearranging here. And so we have pi r squared times our pressure difference, which is really what we're after here. Is solving for this is equal to the weight plus the frictional force plus these terms here. Then next, this pressure difference here is just delta P is equal to the weight plus the frictional force over pi r squared plus 1/3 rho v1 squared. We just basically divide both sides through by pi r squared, and we wind up with this. And we use the result for the weight that I calculated earlier, and we can cancel out these pi r squareds here. And what we find for the final result is that the pressure drop from the bottom to the top is just rho GL. This should make sense, is that we have went up, and this here is just the hydrostatic pressure drop. So if you were to apply fluid statics, that is what that pressure drop would exactly be. But also there is a pressure drop due to the frictional forces acting on it. And we also have the change of momentum. That is, the velocity profile going in is perfectly flat like this, and the velocity profile leaving through the top has actually accelerated in the very middle of it. Okay, and so we have changed the momentum of the fluid, and we've accelerated a portion of it. And the only forces that can do that are actually the pressure forces acting on it. And so that net acceleration comes at a cost of pressure. Okay, and so this is just one example, and you'll get a lot more experience with this moving forward.